Hi, I'm Steve. I make traditional roguelike video games in Rust. These are games where it's a grid of squares. Usually the graphics are all done with text. Maybe you can run it in your ANSI terminal. And normally these are like dungeon crawlers where you descend into a procedurally generated dungeon and try to retrieve some ancient item of power or something. So I've been making games in Rust, these kinds of games in Rust for about 6 years. And over that time, I have built many crates that serve all the various different problems that one faces when building a traditional roguelike. One of those crates, probably the most important one, is called Chargrid. This is short for a character grid because all of the games that I make only use text for their graphics. They run in graphical windows because I'd like people who don't use Unix terminals to be able to play them. But the graphics are made entirely of characters. And so I've built this library called Chargrid, which abstracts away the specific runtime that the game's running on and just gives the game an interface to rendering grids of characters and also getting I/O from the different places. You can play these games on Windows, Macs, and Linux, and in a web browser and in a terminal if you want. And Chargrid takes care of handling all the differences between those different environments. But in order to make your game run in all of these different environments, one of the constraints is that the flow control that the engine uses has to be entirely tick-based. There's no way to spawn a new thread and wait because in WebAssembly, which is what's used to make the game run in a browser, there's no mechanism, or at least the mechanism is different enough from native threads that there's not really a nice way to provide like a threading API to Chargrid. So this means that all of the games have a giant loop around the outside handled by the runtime that just progresses and iteratively ticks the state machine to update the game state, to do all the rendering, and so on. And it turns out that programming in an entirely tick-based environment is a little unpleasant. It's often the case that you'll want to sequence events, like pop up a menu, have the player choose, say, an upgrade for the character or something from that menu, and then maybe have another prompt that says, like, are you sure? And then they press Y, and then the game continues, or something like that, some sort of sequential operation. But in a tick-based environment, all you can really do is add additional states to a state machine, and this quickly gets out of hand. So I'm going to describe a solution that I came up with for this problem, which takes the form of a pseudo-synchronous domain-specific language embedded in Rust that allows you to write code that looks like synchronous blocking code, but actually generates state machines that can be executed in a fully tick-based environment. So this is the common interface that all of the components of one of my games implement. I say game, it's more like the game UI, right? Like the menus, like buttons. There'll be one of these for the game itself, but it'll be kind of this opaque blob surrounding some custom code made for the game. So every component, maybe a good example would be a menu. Every component has some kind of output. It can compute a result. So in the case of the menu, that's the selection that the user made from the menu. The component can be rendered, which just populates a frame buffer. And the component can be ticked or updated, which feeds some input event to the component and allows it to update its internal state and to produce some output as its output. So and this happens on every frame. So I suppose I should clarify that for a menu, the output is not just the choice that the user selected. It's an optional choice, because on all the frames where they don't make a selection, you still have to produce some value, so it'll just be done in those cases. So let's have a motivating example. This is a little game. This game exists. It's not very fun, but it does procedurally generate levels, and you can go down the stairs and see new levels. It's endless. You can't win. You can't lose. But you can open a menu, and that's an interesting academic exercise, because now we have to maintain the state of the menu and the state of the game at the same time, and you can choose an item from the menu, and if you choose quit, the game ends. If you choose new game, the game restarts. So let's look at how one might implement something like this using Chargrid. So here's the component that represents the game. I mean, the only really interesting thing here is the game output. So we're going to say that on every frame, the game either produces no output, like none, or the game's over, which is impossible, but pretend, or escape was pressed. So we want, if the game's running and the user presses escape, we want to be able to say, oh, like, stop the game, they pressed escape, like, let's show a menu instead. When that happens, we show a menu. This is a menu. It's got 3 choices, resume, new game, and quit. And similarly, on every frame, it's got to produce an output, so it'll be done if the enter key wasn't pressed. If the user presses like up or down, we want to change which one the current selection is. So internal to this menu type, like its implementation might just have like an integer value that tracks the current selection, say, and like the names of all of the options. And then update's going to pick which, update internal state and return none if they press down or up, say, and return some value if they pressed, I don't know, maybe enter or clicked on one. All right, so that was pretty straightforward, and that seemed completely fine. The problem starts to arise when we have multiple sort of high-level components that we're trying to multiplex between. So one way of doing that would be just by explicitly implementing a state machine like I've done here. So the app has 2 states, game and menu, and when the game is running, we are in the game state, and we forward all the input events to the game, and we render the game, likewise for menu. This isn't completely accurate because in this implementation, if menu was selected, the game object gets trashed unless we save it somewhere, but we want to be able to stash it somewhere for future use. That's handled, but it's out of scope for this talk. So some problems with this approach. The big problem is that this logic for traversing the state machine is duplicated. And this is maybe fine for a simple thing like this, but if we start adding more menus or having like sequences of menus that are displayed one after the other, this quickly gets out of hand and they'll get out of sync, and it'll become a nightmare to keep them in sync as you're adding features. One of the main things I use this engine for is game jams, and you don't want to have to spend ages messing around with state machines in the middle of your game jam when you're running out of time. The other problem with this is that it's just a little bit tedious when you want to describe a sequential sequence of events in state machines. Like, if I want to add like an "Are you sure?" dialogue after the new game button is chosen, here I need to add a whole other state, wire it into all the different functions that traverse the state. There's no static checks that I've done it correctly, and like it's just a bit of a mess. Like no one enjoys that kind of programming, right? So let's take a look at how we might want this to look in the ideal world, and then we'll see how it actually looks in the real world. So ideally, there'd be a game loop that iterates forever and runs the game until either the game's over or escape is pressed. And then if escape was pressed, it shows the menu. And then that effectively blocks until the choice is made. And then we handle the choice. And then if the choice keeps the program running, we repeat, right? That's nice, but as I said at the beginning of the talk, this would require some sort of blocking flow control, which is not really an option for us if we're trying to be cross-platform. So instead, Chargrid now has an API I call control flow, which allows you to write code kind of like this. So structurally, it's quite similar to the synchronous version on the previous slide. There's an outer loop. It runs the game until the game yields control back to the outer loop, at which point we check what the reason was for exiting the game, and if it was escape being pressed, we do a similar thing with the menu. And then we handle the selection from the menu. And then you'll note these break and continue statements are now just values like in the domain-specific language, and loop is just a function instead of a control structure. And the important, I guess, takeaways from this slide that sort of make the whole thing work are the combinators and then and map. There it is. So if you're familiar, I mean, this is a very similar idea to your futures, say. We have these values that represent computations that we can sequence additional computations onto. This is also, if you're from a functional background, this is a monad. I promise I won't say that word again, or try to explain what it means. So let's take a look under the hood. This is a very tiny snippet of the implementation of the control flow API. So it adds this wrapper, CF, which stands for control flow, which just wraps a component and adds a bunch of additional methods, these combinators for sequencing and doing computations on the results of components. Let's see, what's worth talking about here? I mean, really, this is just an implementation. All the combinators really just return values of these structs, like and then implements components, or and then's a component that composes additional components that do perform computations on the results of other components. And that concludes the talk. So that was a very, very high-level overview of the control flow API in Chargrid, which solves the problem of managing state machines for you in a pseudo-synchronous looking embedded domain-specific language. If you want to check out some of the games that I've made that use Chargrid, you can go to my itch.io, just here, or you can follow me on Twitch, which I occasionally stream myself programming games in Rust, usually in Chargrid. Or you can check out the Chargrid source code on my GitHub. All right, thank you. That's it. Interesting. Yeah, the question was if I had considered writing a custom derive for the type that would give some sort of like traversal code generated automatically. The answer is no, I hadn't thought about that at all. It's a great idea. I'll think more about that. Yeah. So the question was if I had considered using futures instead of implementing my own, or re-implementing the same basic idea, and just polling the future instead of calling update. And you're right, this is something that I had considered. I came up with this idea when I was doing a lot of functional programming that, like with futures basically, and thought, hey, like this sounds like a good fit for this problem. I thought about implementing my own custom futures runtime for Chargrid, but it seemed like I would have to write a lot of unsafe code, and I was just a little bit scared of that. Definitely, and also it would be, I elected not to explore that because currently I like how explicit everything is, and there's sort of no global magic that makes the thing run. And I thought, this was a few years ago, I haven't really revisited it since, but I thought that I would have to do some sort of global magic in order to make it like ergonomic to program like this with futures. But yeah, like it's a very valid idea. Like it's definitely something worth considering.